we're going to do question 9. So the statement here says that in the diagram below, we have points A, B, and C, and D of the circle here, and we are told that OB intersects AC at M and the midpoint of chord AC, right? So, and we're also told that BDC is equals to X. So this angle of D is equals to X, which is this one here. So now we're going to solve the following questions. So 9.1.1 says that we must determine with reasons in terms of X. So now we're going to do A, find the angle of O1. So as you can see from the diagram, this is O1, right? And if you see clearly, I'm just going to mark this point here. So if you see clearly here, you would notice that this is actually theorem 3, right? Remember, theorem 3 looks like this, and then it looks more like a kite, and like that, where the angle at the center is twice at the circumference. So the same thing happens here, where this angle at the center, which is O1, is twice the angle at the circumference, which is X, right? So angle O1 is going to be equal to twice X, because the D is actually equals to X, right? This D here, you can call it CDB, right? That angle which is equals to X, you can call it that way. So O1 is equals to 2X. Reason is angle at center equals to twice its circumference. So that is the reason for the first answer here. So now we're going to do the B part of the question. So now we're going to do find the angle of ABO. So now we know that this middle here is 2x, right? This O1, and we want to find this angle here, right? Because we are told it's what? It's ABO, right? So it's ABO. So basically we want to find angle B, which is equals to angle B1 plus B2, right? So we want to find angle B. So for us to find angle B, we first need to identify the angles that lie inside this triangle here. So if you look at this triangle here, we can use this triangle to find angle B. But for us to first use it, we know that here it's going to be 90 degrees, right? And we need to find this angle here, and then we'll be able to find this angle of B, right? So let me erase everything. So now we're simply going to find angle A first, right? We need to find this angle A, then we know angle M is 90 degrees, then we'll be able to find this one here. So if you take a look, I'm just going to draw this here. Sorry. So I'm just going to draw a line so that you guys can visibly see when I solve this problem. So I'm going to do this, right? I hope you can see this theorem. This is angle on the same segment, right? So meaning that this angle here is equals to this angle here, and then this angle here is equals to this angle here, right? So basically, so this means now that angle A1 is equals to this angle D. So I'll call this D2, right? Equals to angle D2, right? Which is equals to X. So reason for that is angles on same segment, right? Remember, I want to find angle B, which is the combination of these two. So now that we found A1, we're going to use the triangle. So let me erase everything now. I'm going to use the triangle that I'm just going to shade now, which is this one here. So we're going to use this triangle to find B. Alright, so you're going to say in triangle AMB. So now we're focusing on this triangle. We know that A1 is equals to X. M, what is angle M? It's actually equals to 90 degrees. Why am I saying it's equals to 90 degrees? It's because this chord here is perpendicular to this radius here. So it's theorem 1, right? So if they're perpendicular, then it's 90 degrees, right? So that is the reason. So you can write it down. Here you can say radius perpendicular to chord, right? And now we can find angle B, right, which is what is needed. So which you can write as ABO, sorry. So which is ABO plus angle A1 plus angle M is equals to 180 degrees. So this is the sum of angles of interior inside a triangle, right? Sum of angles of a triangle, basically. So meaning, okay, this is 90 degrees, and we know that this is unknown, so we're going to leave it like that. ABO plus our A1 is X plus our 90 degrees here equals to 180 degrees, right? So we're going to transpose these two here to the other side. We will have ABO is equals to 180 degrees minus 90 degrees minus X, right? So this means now that angle ABO will be equals to 90 degrees minus X. So this would be the solution for this question here. Okay, so now I'm going to do 9.1.2. We are asked to prove that AB is a tangent to the circle that passes through ADR. So let's first look at that circle that passes through these points ADR. So let's draw that circle. It will look something like this, and this would be our A point, this would be our D point, this would be our R point. So it's A, D, R. And then the line of AB, so this is A, this would be B, this would be the tangent, and then it will look like this. So basically we are asked to, for us to know that this is actually a tangent, AB, this angle here must be equals to this angle here, right? So basically this D, so it's D1 here and A1. So A1 must be equals to D1. Therefore, AB would be a tangent. So that's what we need to prove, right? Because we can't simply say A1 is equals to D1 and tan chord, because we haven't established that as yet. So we need to prove this in a different way, find that possibility as we calculate. So the first thing you can do here is this. We can focus now, let me erase this first. So this is what we're proving, just don't forget, we're trying to prove this. So what we're going to do is this. We're going to underline this triangle here. I want you to see this one here. So the first thing you're going to do is say in triangle BOD, right? We're looking at that triangle. D2, angle D2, which I call this D2, is equals to B2 this angle here is equals to this angle here, right, which is equals to x. So reason for that is because OD is equals to OB. So it's a radii, or you can just say an isosceles triangle, because this side is equal to this side, therefore the base angles are equal. Cool. And then another thing we can do is, because the whole point here is to make sure that this D1 is equal to this A1, so we're trying to find that out. Please don't forget. So now what we're going to do is this. So for us to continue doing that, we first have to prove that this is actually 90 degrees here. So how are we going to do that? So let me erase this so that everything is clear. So now what I'm going to do is this. I'm saying M1 or M1 equals to M2 equals to 90 degrees, right? And I said the reason was that the radius is perpendicular to the chord, right? So hence that is 90 degrees, right? So meaning this is also 90 degrees. So everything here is 90 degrees. Cool. And another thing is this. So remember that I said this is equals to that, right? So the whole aim now, I'm trying to prove that this B2 is equals to this D1. So for me to do that, these two lines must be parallel. So I can't just say they are parallel unless I prove that they are parallel, which is what I'm doing now. So now I know that this is 90 degrees, right? And another thing is this. If you take a look at this line here, this is a diameter. So DC is actually a diameter, right? Why am I saying that? OD is the radius and OC is the radius. So this is a diameter, and this diameter goes to the circumference like this. So it goes to the circumference. So if you remember clearly, when a diameter does this, when you have a shape like this, and this is a diameter, this one here, therefore here it's going to be 90 degrees, right? Angles on a semicircle. So angle DAC is equals to 90 degrees. Angles on semicircle, right? So this being 90 degrees means this is also 90 degrees, which is what we proved before here. So therefore these two angles are the same, right? They're 90 degrees here, and here it's 90 degrees, making them corresponding angles, right? So once these two are 90 degrees, it confirms now that these two lines are parallel. So therefore OB is parallel to DA. So now we've proven that these two are parallel. So once these two are parallel, then B2 will be equals to D1. Remember that B2 is equals to X. So B2, angle B2 is equals to D1. The reason for that is alternate angles equal, right? So these alternate angles equal, so basically these angles are equal now, and once these are equal, remember that this is also equal to this one here. So since this is X and this is X and this is X, then we are done, because remember we said remember the previous question, we said A1 is equals to X. So A1 was equals to X, and now we just found that B2 is equals to X, of which B2 is equals to A1. I mean is equals to D1, sorry, D1, which is alternate angles, right? So the fact that they are alternate angles, so this is X, this is X, this is X, and this is X. So A1, so you can just conclude and say A1, angle A1 is equals to angle D1, and then you write proven above. right? And so once you do this, then therefore AB is a tangent. Why am I saying that? I said initially we need to prove that A1 is equals to D1. Why? Because when these two are equal, and when this is a tangent, then tan chord theorem applies. But we just proven that they're equal without using the tan chord theorem. So therefore, AB is a tangent. So you have to write a reason for this. You have to write tan chord theorem. Right, so next to this solution here, just write tan chord theorem. Right. Okay, so now we're going to go to 9.1.3. So we are asked to prove that AD squared is equals to 4DO squared minus 4AB squared plus 4MB squared. So this is a bit tricky. I need you to focus on a triangle that supports Pythagoras theorem. Right, because these everything here is squared, right? So let's look at our shape here. So if you take a look, this is supporting Pythagoras theorem. This triangle here, because it's 90 degrees here, we just proven in the previous question, and also this triangle here. Let me write it nicely. So it also supports Pythagoras theorem. It's 90 degrees here. So you're going to use these two triangles to usually prove what is stated in this question. So if you look at the triangle that is pink, hopefully that is the color, triangle ADC, this triangle here, if you were to write it in Pythagoras theorem, remembering that this is the hypotenuse, it's going to be DC squared is equals to DA squared plus AC squared, right? And the reason for this, you can simply say Pythagoras theorem, right? And then now, you should remember that what we are required to prove, we need to say AD squared is equals to something. So some of these values are not part of the triangle, they are part of the other triangle. So we need to find a way. So the whole point is to find dA, right? So let me just write this in terms of dA. dA squared is equals to DC squared minus AC squared, right? So I want to find the solution of dA squared, as you can see, or AD squared, whatever you call it. So we need to substitute here some of the values. We're having DC squared. Let's look from the shape DC. So DC is from this point up to that point. That is DC, right? And we know that DC is formed by OD and OC, right? And if we take a look at this problem here, there is OD, or you can say DO. So instead of writing DC, let's substitute it and put OD where there's DC. We know that DC is actually formed by twice OD, right? So meaning where we see DC, we're going to put twice OD here. So it's just going to be dA squared is equals to twice OD all squared minus, so AC. AC is this one here. Let me mark it from this point all the way up to that point here, right? So that is AC. So let me just, but we know that also AC is formed by AM from here to here, it's AM, and MC, right? And then if we take a look, we only have AB and MB, right? But it's wise to substitute AM because, you know, we're still going to use the other triangle. It's just going to be beneficial. So AC is the entire distance from A to C. It's actually twice AM also. So meaning where we see AC, we're going to put twice AM. So it's going to be minus into twice AM all squared, right? So we're going to have dA squared is equals to 4OD squared minus 4AM squared. So now we're having something like this. Let me erase the top. Erase the top. So now that we're having this problem here, it's getting simpler and simpler to solve this problem. So we're having dA squared is equals to 4OD minus 4AM squared. Remember that we are asked to find this problem here, which is AD squared is equals to 4DO squared minus 4AB squared plus 4MB squared. We are asked to prove that this, right? So now we're having AD or DA rather squared is equals to the 4OD squared, which is this one here. So we already covered that portion, but AM is not part of the equation, as you can see here. So there's no AM, so you need to substitute it with something. We know that AM belongs in both triangles. It also belongs to the small triangle, right? So if we were to write it nicely, so this is AM in the small triangle. So if we were to write Pythagoras for the small triangle, we would say AB squared is equals to AM squared plus MB squared. So this is the Pythagoras for the small triangle, right? For the small triangle. So we want to substitute where there's AM because there's no AM in this equation. So we're just going to substitute it there. So we'll say AM squared, transpose this portion to the other side, is equals to AB squared minus MB squared. So when we see AM here in this, we will put AB squared minus MB squared. So we're just going to substitute it here in this AM squared. So meaning we will have dA squared is equals to 4OD squared minus 4 into, so AM squared is equals to AB squared minus MB squared, and therefore final answer, so it's dA squared is equals to 4OD squared, and therefore multiply everything that is inside, so it's going to be minus 4AB squared plus 4MB squared. So this would be your solution for this problem here, which, as you can see, it's similar to what the question required. So that is your final answer. So now in 9.2, we are given this diagram and a tangent LM with a circle, and what's more important is we are told that NQ is equals to WP and NQ is parallel to MP. So for as long as this information is available, in the diagram, then we can simply look at the diagram. But sometimes some information is written here as text and not shown in the diagram. So please just be cautious of that. So 9.2.1. Now we are asked to state with reasons 3 angles that are equal to M2. So we want 3 angles equal to M2. So this is M2, right? We want another angle that is equal to this M2. It is this angle here. So M2 is equals to angle Q, right? It's equal to this angle Q. So the reason for that is alternate angles equal. Why am I saying that? If you take a look, this is the Z, right? So this is the Z. This is parallel to this line. So therefore this angle is equal to this angle. So it's alternate angles equal. Cool. So now that we've proven that these angles are equal, we want another angle. So for us to find, if we take a look at this shape here, this is a triangle. Just going to draw it. It looks something like that. So this triangle, remembering that LM is a tangent, right? This angle here is equals to this angle here. So it's tan chord theorem, right? So we're going to say M4 is equals to Q is equals to M2, right? So the reason for this is tan chord theorem. So now we've proven that M2 is actually equals to Q, which is equals to M2, right? So M4, we just proven that angle, and proven M2, so they are all equal. So now we want the last angle. So if you take a look here, I'm just going to draw the triangle. Take a look at this triangle that is here. It's not accurate, but it looks like this. If you take a look at this red triangle, you'll see that this angle here and the tangent. So it's the tangent, right? And the angle with the chord, it will produce an angle here. So basically what this means is, okay, let me erase this. What this means is M4, angle M4 is equals to W1. So the reason for that, it's also tan chord theorem. So if these two are equal, and you know M4 is equals to Q, which is equals to M, so therefore W1 is equals to M2, right? So we've proven 3 angles being equals to M2. It's W1, it's M4, it's Q. So all 3 angles, right? So we are done with this question here. Now let's go to this one. It says 9.2. Prove that triangle WMV is similar to triangle QMN. Now let me underline, or let me highlight the triangles. Triangle WMV. So there is W, there is M, there is V. So if we draw the triangle, it's going to look like that. And then triangle QMN. So I'm going to do it in red. QMN. So it's Q, M, N, like that. So it looks like that. So we're going to prove the similarity of these triangles, right? So the first thing we can pick up here is this. As you can see, these triangles. This is a chord, right, which is equal to this chord, right? So I'm just going to highlight the equal chords with a different color. So this chord here that I highlighted with this is equal to this chord here. So the fact that these two chords are equal, they'll produce equal angles. So meaning that it will produce an angle here. So this angle here will be equal to the angle that is produced by this chord, which is this one here. So equal chords producing equal angles. So now this means now that M3 is equals to M1, right? Equal chords subtend equal angles, right? So that's the first thing that is similar between these two. And another thing that is similar is this. Okay, so another thing that is similar is this, in these two triangles, is that this W1 here is equals to this Q here, right? And we've proven that in the previous question. So angle Q is equals to W1. So you can simply say proven. So yeah, now we have two angles that are equal. It's M3 and M1, Q and W1. Fine. And another thing you can see here is this angle V. So this is now the third angle. So if two angles are equal, so we just compare two angles, this angle here and this angle here, this angle here and this angle here. So this confirms now that even though we just compared two angles with reasons that they're equal with each other, which means the third angle of the shapes will definitely be equal. So this confirms now that V1 would be equal to N1 plus N2. So this is just the sum of angles of a triangle, right? So yeah, therefore the triangles are similar. So triangle WMV is similar to triangle QMN. So the reason is we just used angles only to prove that. It's angle, angle, angle. Right. Okay, so now 9.2.3, we are asked to prove that MV over WV is equals to MN over PW. I just want to write that down. Required to prove that MV, so let me write it nicely, over WV is equals to MN over PW, right? So the PW is, so you're required to prove that this ratio is equals to this ratio, right? So but before we solve this problem here, we need to remember that in the previous question we concluded that triangle WMV is similar to triangle QMN, right? So if we were to write this in ratio form, you will say this MV here. Okay, let me use another color. So you'll simply say the MV, which is this one here, you'll divide it with this portion here of MN. So it's going to be MV over MN, right? And then you divide it with what's WV. So you see equals to WV divided with QN. So it's going to be divided by QN, right? So what you will do is you'll cross multiply. So it's going to be MV multiplied by QN equals to WV multiplied by MN, right? And we know that QN, which is this portion here, is equals to PW, right? So it's given is equals to PW. So this is given, right? So where we see QN, we want to replace it with PW. Why? Because the previous question there's PW, right? So it's going to be MV multiplied by PW equals to W mv multiplied by mn, right? So let me write it here. So it's going to be mv multiplied by pw is equals to wv multiplied by mn. Now we're going to write it back into fraction form, so meaning we can divide by, because here on our left hand side we have mv, which is this mv, right? It is divided by wv, which is this portion here. So this is multiplication, so we're going to divide by wv, divide by wv both sides, so you will have mv over wv multiplied by pw is equals to mn, right? So we're going to remove this pw because it's at the bottom, as you can see here, and we divide by pw both sides, so we have mv over wv is equals to mn over pw. So this is the expression that is required to be proven in this problem here.